Colligative properties. Colligative properties are properties of a solution that depend only on the number and not the identity of the solute particles. And an example of a colligative property is vapor pressure. We know that when we add a solute to a solvent, the vapor pressure is lowered. And it's dependent on how much solute particle we add, not what the solute particle is. And because phase changes are dependent on vapor pressures, these will affect all our phase changes because they're dependent on vapor pressure. So let's talk about normal boiling point. We know that normal boiling point is the temperature where the vapor pressure is equal to 1 atmosphere. But if a non-volatile solute lowers the vapor pressure, the temperature to boil the substance must have to increase. So when we look at what's referred to as boiling point elevation, it depends on the concentration of the solution. So our equation is delta T, which means the change in our boiling point, will equal Kb times the molality of our solute. So the delta T is the boiling point elevation, how much our boiling point goes up when we add our solute to our solvent. Kb is our boiling point constant for the particular solvent. And that lowercase m means molality, which again, remember, means moles of solute per kilogram of solvent. So here we go. Let's look at a problem. A solution is prepared by adding 31.65 grams of sodium chloride to 220 milliliters of water at 34.0 degrees Celsius. And it tells us that the density for water at that temperature is 0.994 grams per milliliter. And the boiling point constant for water is 0.51 degrees Celsius kilogram per mole. We want to calculate the new boiling point, assuming that the sodium chloride totally dissociates in the water when it dissolves. All right, so let's start with our equation. We know that the change in our temperature equals the boiling point constant times the molality of our solute. So we have 31.65 grams of sodium chloride, which we can convert to moles. 1 mole of sodium chloride is 58.44 grams. But sodium chloride is an electrolyte and it 100% dissociates, so for every 1 mole of sodium chloride, we're going to have 2 moles of ions. So the molality of our particles then is 1.083 moles. Now we're going to take the 220 milliliters of water, and we're going to be able to first convert that to grams because it tells us that the density is 0.994 grams per milliliter, and we know that there are 1,000 grams in 1 kilogram. So we're going to have 0.2187 kilograms of water. So our boiling point is going to be changed due to the constant, so we'll put that in 0.51 degrees Celsius kilogram per mole times 1.083 moles of solute per 0.2187 kilograms of solvent. So our boiling point is going to change by 2.53 degrees Celsius. And we know that by adding a solute to a solvent, that lowers the vapor pressure, which increases the boiling point. So pure water boils at 100 degrees Celsius. So we're going to add 2.53 to that, and our new boiling point is going to be 102.53 degrees Celsius. Now when we talk about freezing point, we know that freezing point occurs when the vapor pressures of the solid and the liquid state are equal. Since the vapor pressure is lowered when a solute is added to a solvent, the temperature has to be lowered more in order for the vapor pressure to become equal. So we're dealing with what's called freezing point depression. When we add a solute to a solvent, the freezing point temperature goes down. Now the equation looks just about the same as our boiling point elevation equation, except that this time we've got our delta T is the lowering of the freezing point, Kf is the molal freezing point constant, and our lowercase m is the molality of the solute. So let's do another problem. How many grams of glycerin, and it gives us what the formula for glycerin is, must be added to 350 grams of water in order to lower the freezing point to negative 3.84 degrees Celsius? And it tells us that the freezing point constant for water is 1.86 degrees Celsius kilogram per mole. All right, so first we have our equation. We've got delta T for our freezing point equals Kf times the molality of the solute. Well, it tells us what the freezing point temperature changes by. 3.84 degrees Celsius. And that's an absolute value. We're going to plug in 1.86 degrees Celsius kilogram per mole. We don't know how many moles of solute we added, but we do know that we have 0.3500 kilograms of our solvent. So we're going to be able to go through and solve for our moles of solute. We're going to divide both sides by 1.86. We're going to multiply both sides by 0.3500, and that's going to give us 0.723 moles of solute. We want to know how many grams, so 1 mole of our solute equals 92.11 grams, since it gave us the formula, and that's going to give us 66.6 grams of C3H8O3 must be dissolved in 350 grams of water in order to lower the freezing point 3.84 degrees Celsius.